Uh, Good evening and welcome to the February New Bedford Science Cafe. I'm Bob Rocha, Director of Education and Science Programs at the New Bedford Whaling Museum. I'm happy to welcome all of you here, and it's great to see all of you participating. It's fun to look down and see the number of participants continue to climb as we get this started tonight. So, and I want to note that our next Science Cafe in March will be March 2nd. It will feature ornithologist Alan Poole. He'll be coming in live from Costa Rica, and his focus will be the Quetzal, birds as barometers of land use in Central America. But before we get to that, I would like to tell you about tonight's presenter and get this thing off my screen. Thank you very much. All right, tonight's presenter, and let you know that once we are done with Dr. Francis's presentation, colleague as part of the New Bedford Science Cafe team, Grant O'Reilly, will be moderating the Q&A. There's Grant. And as always, thank you to my colleague Jocelyn Nunes from the New Bedford Whaling Museum for being behind the scenes and keeping an eye on all things technical related to tonight's presentation. So, Jennifer Francis is a senior scientist at the Woodwell Climate Research Center, formerly the Woods Hole Research Center in Falmouth, Massachusetts. Previously, she spent 24 years as a research professor in the Department of Marine and Coastal Sciences at Rutgers University, where she studied the Arctic climate system and how rapid Arctic change is affecting areas beyond the Arctic, particularly extreme weather in the Northern Hemisphere. She is regularly interviewed for radio and TV news programs and is often quoted in major media outlets. In 2020, she testified to the U.S. Senate Subcommittee on Security. In 2019, to the House of Representatives Science Committee, and in 2013, to the Senate Committee on the Environment and Public Works. She has taught courses in satellite remote sensing and climate change issues, and also co-founded and co-directed the Rutgers Climate and Environmental Change Initiative. Jennifer earned a BS in meteorology from San Jose State University in 1988 and a PhD in atmospheric sciences from the University of Washington in 1994. She and her husband circumnavigated the globe by sail during the early 1980s, including the Arctic, which is where her interest in the region began. So, live from a boat in the U.S. Virgin Islands, I give you Dr. Jennifer Francis.
So, tonight we are talking about the Arctic, the fact that it's warming so fast, the ice is melting so fast, and why a place that's so far away, way up to the far north, should matter to any of us who live down in the lower latitudes. Well, I want to start out by just remarking that this was a phenomenal year, 2020, in so many ways, but one of the ways is that there was a record number of billion-dollar extreme events, and that it was a record number in the US itself, but also worldwide. So Mother Nature just threw a tantrum this year, and maybe kind of along with a lot of the other things going on in our world, it seemed to just kind of fit in with 2020. But this image that you're looking at right now is one of the hurricanes that hit the Gulf Coast. So this is the Gulf of Mexico down in the bottom here. And what we're looking at is basically the confluence of two extremes at the same time. We've got this hurricane hitting Louisiana. This was Hurricane Sally. And over the continent here, the United States, you see this incredibly thick and expansive layer of wildfire smoke that has come all the way across the country from the western states. And as you know, it was a record-breaking year for forest fires out in California and other states, Colorado, and also a record-breaking year for the number of hurricanes that struck the United States. So it's just kind of an emblematic image I'm showing you here. But it's part of a bigger story that's happening around the world. And what you're looking at here is a chart showing the frequency of extreme events that caused more than $1 billion in damage. Of course, those dollars are corrected for the year. And there are 4 kinds of events shown here. I want you to focus on the fact that the red events down at the bottom, going back to 1980, these events are associated with things that don't involve weather. So think about earthquakes and tsunamis and volcanoes, things like that. But all the other things are weather related or climate related. And what you notice is those weather related events are increasing. In fact, they've tripled in frequency just since the early 1980s. This is being measured not just by scientists, but also by companies like insurance companies. This is one of the biggest insurance companies. It's a reinsurance company, actually. So they really care about these things because they cost a lot of money. So let me just take a step back here and set the stage of where we are. This is looking at the last 20,000 years of global temperatures, of course, reconstructed from various types of data like tree rings and things like that. And so 20,000 years ago is on the left, and we go towards present day, towards the right. So back in 20,000 years ago was the last time we had an ice age, and that's why the temperatures are so cold. Notice they're only 3 degrees colder than basically present day average temperatures. And then about 8,000 years ago, we had what we call the last interglacial, or a warm period in the Earth's climate cycle. And since then, since 8,000 years ago, the Earth has been actually getting cooler. And all of these processes here that cause this change in the global temperature are all natural. So there weren't many humans until very recently in this graph. But as we can see, and as you all know, in the last 100 years or so, the temperature has stopped going down as it would be now if only natural causes were happening. And instead, it's shooting straight up. And of course, you all know that this is because of all the extra, especially carbon dioxide and other greenhouse gases that we've been dumping into the atmosphere. And as we look to the future, by the 2100, we see that temperatures are probably going to be between 2 and 3 degrees warmer than they were before we started basically the Industrial Revolution. Now, remember that I said the last ice age was only 3 degrees colder than average, than normal for right now. And 3 degrees warmer than that is, that's not a lot. That doesn't seem like a big change in temperature, but you know what the last ice age was like. The ice sheet was all the way down across most of halfway down the eastern seaboard. So it doesn't take much of a temperature change on Earth to make some pretty big changes in our climate system. And we're already starting to see that. But if we look at how temperatures have changed, especially recently, around the globe in spatial form here. So this is a map showing how temperatures just in the last couple of decades compare to previous times. You can see that it's certainly not even. And the warmest areas, the places that have warmed the most, are the far north, the Arctic. And the temperatures there are rising about 3 times faster than the globe as a whole. This is something we call Arctic amplification. You've heard a lot about temperature. You don't hear so much about water vapor. Water vapor is a very underappreciated story, in my opinion. And what you're looking at here is really just a kind of eye candy for water vapor. It's from this past summer, so the summer of 2020. And we're looking at the whole globe and an animation just for one day. But you can see all kinds of interesting things. So here's the tropics. All these bright orange colors are showing where the most water vapor resides. If you've ever been to the tropics, you know it's very sticky and moist. And there's all kinds of interesting features happening here. So here's Bermuda. You can see this little spinning blob here. That was Hurricane Teddy, which made a very close call to Bermuda in September this year. There was another tropical storm moving up into the Gulf of Mexico, another one off the west coast of Mexico, and a couple of others out here in the Western Pacific. So lot of water vapor in the tropics, of course, but you can also see these really interesting tendrils of water vapor that are being stretched towards the poles. And that's the job of storms. So you see along a front, for example, a weather front, you get the water vapor being pulled to the north. The reason this water vapor is so important is because water vapor is one of those greenhouse gases. And as we warm the air and we warm the ocean, because of the carbon dioxide and the non-natural greenhouse gases that we're putting into the atmosphere, we're seeing more evaporation from the oceans, and it's adding more water vapor to the air. So this is a greenhouse gas, so it is a positive feedback or a vicious cycle that's adding to the warming that's happening because of those fossil fuel-based greenhouse gases. And as a result, we're seeing a steady increase in the amount of water vapor in the global atmosphere. In fact, it's already increased about 7%, which is just what we'd expect to see for a global temperature increase of about a degree. So not only is that water vapor a greenhouse gas adding to the problem, but it also provides the fuel to energize storms. Storms really feed off of that water vapor. They use that as their energy to get stronger. And of course, if you've got more water vapor in the atmosphere, you're going to have more precipitation. And one of the clearest signals of climate change is the increase in frequency of heavy precipitation events. And in this graph, you can see that these changes, just since the 1950s, the period between the 1950s and the 2000s, we've seen really big increases in the frequency of these heavy downpours, especially in the Northeast. You can think back to that storm we just had a couple days ago and that very heavy snowfall. Okay, we're going to shift gears now and talk more about the Arctic. And I showed you the map of how the Arctic is warming faster than the globe as a whole. Well, here's a graph that shows that in another way. Going back to the late 1940s, this is how the Arctic's temperature has changed during the summer. And this past summer, we set an all-time new record for the temperature of the Arctic, going back as far as we can see. In fact, we can look back almost 2,000 years, and we are definitely seeing the temperatures warmer there than we've seen over that entire time period. In fact, it's now off the charts. And why is this important? Well, it's partly tied to the loss of the ice that's floating on the Arctic Ocean. This animation is showing you how the thickness of that sea ice floating on the Arctic has changed since the late 1970s. Those bright white and yellow colors are showing you where the thickest ice is. So it tends to be along the coast of Canada and the north coast of Greenland here. And as we go through time, you can see that very thickest ice types, when we go back to the early 1970s and compare it to where we are today, there is really no comparison. The thickest ice types are basically gone. So what do we think is going to happen with this ice, and why do we care about it? Well, first let's look at what we expect to see happen. So this is an interesting plot because instead of having years on the bottom of the graph here, which is more typically shown, we're showing global average temperatures. So here we are today at about a little over 1 degree warmer than average. And we can see that we still have, during the summer months here, so you've got the months of the year on the vertical axis, you can see that we still have some ice in the summertime. But as the global temperature gets up to about 1.7 degrees C, now remember we're already up to about 1.25, so we don't have far to go to get to 1.7. That's when we expect to start seeing the Arctic become ice-free in the summertime. So basically, all of the ice gone, maybe just a little bit left along that coast of Greenland there. And then after that, as the Earth continues to warm, we're going to see that ice-free period cover more and more months. So not only is the ice not only losing the thickest ice, we're also losing the aerial coverage of the ice. So these two figures here are showing you what the typical ice cover looked like back in the late 1970s during the summertime when it's at its smallest. extent, and compare that to what it looked like in September of 2012, when we saw the least amount of sea ice ever recorded. That was the record. By the way, we came very, very close this past summer to beating that record. So the last several years have looked almost exactly like this. These orange colors here are showing you where the ice used to be. Now this is really important because, of course, this ice is very white and it reflects most of the sun's energy that hits it. And so by losing all of this ice in a very short time, in only about 40 years, we are actually making the Arctic darker. Because now, instead of the sun's energy being reflected by the ice that used to be here, it's now getting absorbed into the ocean. And it's warming that water, and it's warming the Arctic as a whole. You can think of this loss of sea ice as what I'd like to call a threat multiplier. And that's because by losing all that ice and absorbing all that extra heat from the sun, we're actually increasing the warming of the globe as a whole by somewhere between 25 and 40%. It's been estimated in some recent work. So it's making global warming worse. It's increasing the rate of melt of the Greenland ice sheet, which of course contributes directly to sea level rise. It's thawing the permafrost. This is the frozen soil that exists in the far northern areas. And as we thaw that permafrost, the organic matter that's frozen in that soil is now being decomposed by microbes, and it's releasing even more carbon dioxide and methane into the air. So this is another one of those vicious cycles that's happening in the climate system. And finally, this is a more, I'd say, controversial and new research that's been going on that I've been working on in particular is how the rapidly warming Arctic is affecting the winds of the jet stream. And the jet stream is what creates and steers our weather patterns. So let me explain that story. So here we are on Earth, and I want you to think about a layer of the atmosphere extending from New Bedford all the way up to the Arctic. Now, we know that it's warmer in New Bedford generally than it is in the Arctic, and we know that warm air expands. So this layer of air is going to be thicker. It's going to be taller, if you will, in New Bedford than it will be in the Arctic. So if you were sitting on top of this layer and looking towards the north, it would look like you were looking down a hill, which in fact you would be. So the air up there wants to flow down that hill just like water wants to flow down the side of a mountain. And this creates a wind. So that wind is, of course, blowing from south to north because that's how the hill is tilted. But because the Earth is spinning, that wind gets turned to the right. Everything in the northern hemisphere that's moving has a field of force that turns it to the right. And this creates what we call the jet stream. Now think back to that Arctic warming much faster than it is down here in New Bedford. What's happening is that layer is getting thicker faster in the Arctic than it is down here farther south. And so the tilt of that hill is getting less steep. So the force driving that wind is getting smaller. We're seeing that flow towards the north getting weaker, and this is causing the jet streams to also weaken. And that we know that when the jet stream is weaker, it tends to take these bigger meanders north and south. It's more easily deflected by mountains and by blobs of warm water in the ocean, for example. And so we get these bigger north-south waves in the jet stream. And this is what it looks like in a more schematic way. So on the left here is an example from November 2013 when the Arctic was very cold. You can see that blue color sitting on top of the North Pole. And these red arrows are showing you schematically what the jet stream looked like on that day. It's relatively straight and flowing directly around the Northern Hemisphere. And here's another example in January of 2014, when very much like what's going on right now, we had a very warm Arctic then. These blobs of cold air were descending southward over the continents and creating long cold spells. And what you see the jet stream doing is taking these bigger north-south waves as it travels around the northern hemisphere. Now, these waves are really important because when they get large like this, they tend to move much more slowly from west to east. And because they're responsible for creating the weather that we experience, the weather also moves more slowly. So we tend to get these very persistent weather regimes. And interestingly, if we look at what the jet stream looks like, actually, this is a forecast for a couple of days from now, but it looks eerily similar to this day in January of 2014, which in fact was one of the coldest and most persistent cold spells that we've had in recent years over the eastern parts of the country. And you can see these bright colors here, there's North America right there, are showing you what the jet stream is forecast to look like. It actually looks very similar to that right now, but it looks very, very similar to this case over here. So the reason why I'm spending so much time talking about these waves is because, as I said, they have everything to do with our weather. So here's a schematic of one of these waves in the jet stream. It looks very similar to what we've got happening right now. The jet stream separates the warm air to the south from the cold air to the north. So if you're north of the jet stream, it's much colder than it is if you were to the south of it. But in addition to that, these waves create dynamics in the atmosphere that cause this part of the wave, where the winds are coming down from the northwest, to create high pressure at the surface. And that tends to be very dry and settled and clear skies. Whereas this part of the jet stream, where the winds are coming from the southwest, is where we tend to get our storms. And as I said, it looks a lot like this right now. That storm that we just blew through yesterday is being propelled and generated by a jet stream that looks very much like this. So just happened to work out that way. Now, sadly, the real jet stream is not simple at all. It doesn't look like that nice schematic that I just showed you. But you can see in this animation of real winds high up over our heads, where the level where the jets fly. These yellow and red colors are showing you where the fastest winds are, which is telling you where the jet stream is. And a couple things I want you to notice. First of all, just how messy it is. So trying to do some research on figuring out how the jet stream might be changing over time. But also notice when the waves are small like this, they tend to move quite rapidly across the country. But when they get large, they tend to get stuck in one place and linger for a long time. So that's one of the things I want you to remember from this presentation tonight, is when the jet stream has these big waves in it, we tend to have very slow moving weather regimes. We tend to have these very persistent weather conditions, just like you all have experienced the last week or so, with very, very cold temperatures. Okay, so just to get towards the end here, I wanted to show you a couple of examples, of recent examples. This is from January, early January to mid-February. So that's like 5 weeks in 2018, when it got very, very cold in the east. It snowed in northern Florida. There were iguanas falling out of the trees because they were basically in comatose state because of the cold. So what did the jet stream look like when this was happening? Well, you can imagine it in your head probably. It's looking a lot like what it is right now, with one of what we call this a big ridge over the west that allows the warm air to penetrate way far north, and then a dip, which we call a trough in the jet stream, that allows the cold Arctic air to penetrate way far south. This is exactly what we've got going right now. So this week especially, it's very cold down in Florida. And in fact, the National Weather Service today put out a warning that I've never seen before. They put out a falling iguanas warning. So yeah, it's cold down there. But right after this, starting in mid-February, some of you might remember this, just the opposite happened. So the temperatures along the East Coast rose dramatically. All of these little circles here are circling temperatures that are records for that date in February. You might remember going to the beach if you lived in Boston, for example. And then all the cold air instead was out in the west. So if we look at what the jet stream looked like You can probably guess. Instead of the trough being over the eastern part of the country, instead it was over the west. But in both of those cases that I just showed you, those waves were very large. And so these conditions hung around for a really long time. So just want to bring it back to the present here. I'm looking now at a map of ocean temperature differences from normal. And this is from just yesterday. And so these red colors are where the ocean is warmer than it should be, and the blue colors are where it's colder than it should be. There's some interesting features here. First, there's blue tongue here. As you probably know, we're in the middle of a moderate La Nina condition, which is when we get this tongue of cold water stretching across the tropical Pacific. And we have this really large area of warm water that's been hanging around in the North Pacific for quite a long time. Now, if you think back to that diagram and explanation about the hill in the atmosphere, think about what these ocean temperature patterns are doing to that hill. So we've got this warm, extra warm water sitting in this area and cold temperatures to the north. So along that boundary, it's actually making that hill deeper. So that is increasing the winds of the jet stream, and it tends to favor having the jet stream follow that gradient or that barrier between the cold and the warm water temperatures and bring that jet stream not into California, but up into British Columbia. So it tends to form one of these northward bulges in the jet stream when we get this kind of an ocean pattern. It then will dip down, which is exactly what it's doing right now, and then follow that same kind of thing out into the Atlantic. So sometimes we can just look at what the ocean temperatures are doing, which don't change very fast, and we can get a pretty good idea of what the general jet stream is going to do for the next weeks to months. And just to talk a little bit about the storm we just had, these nice graphics showed up on the CBS website. You've heard a lot about the stratospheric polar vortex being involved in the cold temperatures that you've been experiencing. And so the stratospheric polar vortex is sort of like the jet stream, but it's much higher up in the atmosphere. It only exists during the winter months, and normally it's the winds that flow around the stratospheric polar vortex are basically forming a barrier to very, very cold air that sits on top of the North Pole. But what happened 2 weeks ago was that air in the stratosphere underwent what we call a sudden stratospheric warming. And it actually warmed up about 100 degrees in a very short time. And that creates a big disruption in that upper level wind pattern that when it happens, when that stratospheric polar vortex gets warm like that and gets disrupted, we know that crazy weather is going to happen soon thereafter. And sure enough, of course, by having that barrier broken in that stratosphere, it has allowed the Arctic air to plunge right down into the eastern part of the United States and also down into parts of Eurasia. And as we can see, the jet stream that goes along with that looks just like what I showed you. And this is where our storm formed in that part of the jet stream where the winds are coming from the southwest. And it brought a lot of that moisture in from the Atlantic, overriding that cold air, which is why so much snow fell in northern New Jersey, eastern Pennsylvania, and eastern New York. It was quite a snowstorm. All right, so just wrapping up with a look into the future here. What's going to happen to our summer sea ice extent? We already talked about it a little bit, but we do have some choices here. So what you're seeing here is a combination of actual changes in the Arctic sea ice extent going back to the late 1940s and up to about present here with this black line. The other stuff is all simulated by these very complicated computer models that we use to try to understand how the climate system works and also project what's going to happen in the future, making various assumptions. So what you can see is that as these computer simulations going back in time actually are very similar to what the real world has done. And as we go forward, these different lines of different colors here are based on different assumptions about the future. So this red line here is what we call the worst case scenario, which is what if we do nothing about curbing our emissions of greenhouse gases, if we don't stop cutting down all the forests. This is what we expect to see. And as I already mentioned, we expect to see the Arctic go ice-free sometime around the middle of this century, possibly as soon as 2040. But if we do get our act together and we are able to really cut back on emissions of greenhouse gases, we can prevent the Arctic from becoming ice-free in the summer. We can prevent a lot of the extreme weather events that are on the rise now, and will continue to rise for a while, because you can see that even all of these colors are basically on top of each other until we get to the middle of the century, and that's when we start to see differences in the effects of differences in our behavior. But this is saying there's hope. We're still going to see a lot of changes in the climate system. There's still a lot of warming, a lot of melting, but we can make it much better than if we do nothing. And this was the view by the son of one of my PhD students at Rutgers. He sent me this painting that he did, and it really struck me that this was his view of the future. And I sure hope that we can do better than this for his generation. And there's a lot of hope right now. If we were having this conversation several months ago, I would not be quite so hopeful, but I think there is a chance that we can make this world maybe not disintegrate for our kids and their kids. So thanks very much. I'm looking forward to your questions. And I'm hoping that all worked.
Jennifer, it did all work. That worked out actually really nicely. There wasn't much glitchiness, if at all. Grant,
Great.
there are some questions in the chat, so you guys can go ahead and transition to that Q&A.
Great, thank you, Jocelyn. First, Jennifer, thank you for an absolutely fascinating talk. In honor of our tradition at Science Cafe, I have a beer here that I'm enjoying during your talk. So, couple of questions, and anyone who has a question, please post it to the chat. Good on you, Robert, that are here. So I'm going to try and pull them out. Oof, lots of questions coming in. I've got just a question to begin with, and I think it relates exactly to your final comment. How do you think that the proposals coming from the new Biden-Harris administration on climate change, which of those different lines on your next to last slide do those sort of proposals correspond to? Are they the aggressive carbon reduction proposals that we need to see, or are they somewhere a bit less than that?
Well, I haven't read those proposals in detail. My guess is they're probably not aggressive enough. They're probably not that green line. That's pretty aggressive. To get to that green line, we're all going to have to do a lot. And one of the most important things that needs to happen is for the emission of carbon into the atmosphere has to become expensive. And it needs to happen at the source. Energy needs to be more expensive for all of us. It really does. We've been enjoying very inexpensive energy for a long time. It's allowed our economy to grow, which has been a good thing. But now we know that it's also been doing a lot of damage. And so, the companies that generate our electricity, that build our cars, they've been dumping greenhouse gases into the atmosphere for a long time and not having to pay the cost of that. So it'd be like, not having to pay to take your trash somewhere, or, it needs to be, the incentives need to be put into place to make it expensive to dump greenhouse gases into the atmosphere. And, we've got the technology, we know how to get away from fossil fuels now. it's already happening. The cost of new power generation from renewables is now cheaper than it is from fossil fuels. So it's really just a question of getting the will behind it. And that gets back to this question: is the will strong enough in these proposals? Well, we'll see. And it's not just the United States. It's, all of us around the world. Carbon dioxide does not stay in the same country where it was emitted. So this is a global community problem. It's not just us, although we are definitely behind the curve compared to many of our developed countries and allies when it comes to getting ourselves into the new generation of energy.
Thanks, Jennifer. I think it's really important that people hear that. And I think it's also important that one of Biden's first actions was to rejoin the Paris Climate Accord. So there are a couple of questions here. Eleanor Denuzo asks, can you explain what causes the increase in water vapor in the atmosphere as global warming takes place?
Sure. So the amount of water vapor in the atmosphere is very tightly coupled to the temperature of the atmosphere. There's actually a limit to how much water vapor can exist in, say, a blob of air based on its temperature. So as you warm the air, it can actually absorb more water vapor. And so what's happening is we're warming the air, we're also warming the oceans and the land. And so there's more evaporation from those warmer oceans and warmer land into this warmer atmosphere. So it's really as simple as that. It's and I mentioned that we've already increased the amount of water vapor by 7%. When you increase air temperature by 1 degree Celsius, you can get a 7% increase in water vapor. That is just very straightforward physics, actually.
Okay, so a second question from Jim Anderson is, the computer models that you talked about, do they capture these permafrost events? And also he asks about methane cathrates that are located in the deep ocean. So are they part of these computer models used to predict what might happen?
That is an excellent question, and the answer is no. The models that were used to create that graph were the previous generation of models, which wasn't that long ago. It was only a few years ago, but those did not take into account the thawing of the permafrost and the release of carbon dioxide and methane from that decomposing and thawing soil. And in fact, this is one of the major projects that my organization, the Woodwell Climate Research Center, is involved with, is trying to understand these processes in the permafrost well enough to be able to turn them into computer code, if you will, so that it can be incorporated into the climate models. So the estimates of global warming from the previous generation of models was probably underestimated because of this process, and some others too that we still don't understand completely. For example, sea level rise models are still not really capturing all the processes that happen on an ice sheet like Greenland, where it's melting from above, it's melting from below, where the ice meets the ocean. Same thing is happening in Antarctica. So, a lot of these numbers are somewhat estimated and most certainly conservative.
Okay. So you talked a lot about the jet stream and changes of that. So there are a few questions on that in the chat. So Rachel Mulroy asks, is there a correlation between how the jet stream is slowing and the strength or frequency of hurricanes? And a similar question about talking about snowstorms. Is the increase in snow related to the jet stream changes?
Yeah. So those are really good questions. When it comes to hurricanes, there is not a lot of connection between what's happening to the jet stream and changes in hurricanes. Hurricanes are responding more closely to changes in the temperature of the earth and temperature of the ocean. So as the ocean gets warmer, we're expecting and we're already seeing an increase in the frequency of the strongest hurricanes, and we're seeing an increase in the frequency of rapidly intensifying hurricanes. But right now, we're not, it's not clear whether we're going to see more hurricanes totally, because there are a lot of other factors that are offsetting the warming effect. That said, there is also evidence that hurricanes are slowing down in terms of their forward motion and how fast they move. And we think that is related to the changes that are happening in the jet stream. So when a hurricane comes up the East Coast, say, far enough north where it can interact with the jet stream, then we're starting to see more of these stalling storms and just slow moving storms. So you can think of Hurricane Harvey, for example, that stalled over Houston and dumped 50 something inches of rain. Hurricane Florence did a similar thing over the Carolinas. Hurricane Dorian recently over the Bahamas. I mean, there have been many recent examples of these very slow moving storms, and there is evidence that that is happening, and that would be probably connected to the slowing jet stream. But for snowstorms, there's a lot of factors to take into account when we start talking about snowstorms. The easiest one to think about is that because I showed that ocean temperature difference from average chart just from yesterday, and you might have noticed that there was a big area of very warm water sitting off the east coast of the United States. So when a storm, especially a nor'easter, forms like we had yesterday, it can tap into that heat in the ocean just like a hurricane does. And not only does that heat and the contrast in the temperature between the ocean and the very cold land that was in place, not only is that fueling the nor'easter, but also there's more evaporation from that warm water. And so that the storm can tap into that moisture and dump even more precipitation onto the land. And so that is one of the reasons why we're seeing those big increases in the frequency of heavy precipitation events that I was talking about. And that warm water sitting off our coast is definitely a climate change story. Oceans generally are warming very steadily. The oceans absorb about 90% of the heat that's trapped by the extra greenhouse gases in the atmosphere. But you'll notice that off the East Coast of the United States, it's really warm. And this is a fascinating story, actually. There's been some very new research that suggests that the extra fresh water that's coming out of the Arctic Ocean because of ice melt and off of the Greenland ice sheet because it's melting faster is creating a lens of fresher water sitting on top of the North Atlantic that is preventing mixing from the deeper layers of the ocean. And it's acting like a barrier almost to the Gulf Stream, which is the warm current that flows up the East Coast. And so it's like backing up a sewer pipe. It's keeping all that heat from leaving the East Coast, and we're seeing it pile up. And for the last 5 or 6 years, we've had those very warm temperatures, which is affecting all kinds of things, including our fisheries and the lobster and many aspects of the marine ecosystem. Long answer, but
yeah. Well, your last part just answered Fred Sterner's questions. So just to stick with the jet stream for a minute, there's a few people, John Garvey and Richard Jacobs, of asking, is there a jet stream in the Southern Hemisphere? And what's happening at the South Pole? Is that disappearing at a similar rate to the North Pole?
That's another great question. And yes, indeed, there's a jet stream down there too. In fact, there's more than one jet stream. I didn't want to get into that, but there's a polar jet stream, which is the one I've been talking about mostly, and there's also a subtropical jet stream. So both hemispheres generally have 2 jet streams. The Southern Hemisphere is behaving very, very differently from the Northern Hemisphere. We don't see the Antarctic, which is in the South Pole, warming anywhere near as fast as the Arctic is. And the reason is because, as you know, the Arctic is an ocean and the Antarctic is a continent. And that continent in the Antarctic is covered by an incredibly thick layer of ice. It's over 2 miles thick in some places. And so the sea ice that forms down there forms only in the wintertime, in the cold part of the year, and it melts all the way back to the coast every summer. So there isn't this opportunity for ice to be lost more and expose that dark ocean, because it already melts all the way to the coast. So you don't have this vicious cycle forming where you lose more ice and more water, and then that sets up this process. So if that's not happening down there, different things are happening down there though. We know that the tropics are actually expanding. So they're pushing northward and they're pushing southward. And so we're seeing the southern jet stream actually retreat farther south towards Antarctica, towards the coast of Antarctica. So it's kind of the, not really the opposite, but it's just a very different set of circumstances down there. This is connected to the fact that Australia has been having such heat waves and forest fires because the jet stream is gone so far south that it's not bringing storms up into Australia like it used to. And so they're just not getting as much rain. Same thing's happening in South Africa and parts of South America, where the rain bands are staying farther south. So it's a complicated climate system we're looking at here.
Thank you. So a few people, Jeffrey Wish and Jean Cole, have asked about, with the pandemic and the reduction in people's travel, both internationally and in daily commutes, has that had a significant impact on both the amount of carbon dioxide in the atmosphere, and going forward, might that be part of the solution to reducing carbon dioxide?
Well, certainly getting our travel behavior to get it under control and to be able to travel but not emit as much carbon dioxide is a really important thing to be doing. We all need to think much more about how much traveling we do, because certainly flying in an airplane uses a lot of fossil fuel. And in fact, it's been estimated that if you fly from London to Boston, roughly, the fossil fuel burned by your being on that plane melts approximately a dining room size table of sea ice in the Arctic, just by one person on one flight. So it's a big impact. But during the pandemic, we did see a reduction in the emissions of greenhouse gases because of things like travel being curtailed, but we still see the concentration of greenhouse gases in the atmosphere increasing. So the story is, if you think of a bathtub and you've got a drain in the bottom of the bathtub, okay, so water can run out of the bathtub at some rate. And if you have a faucet that's putting water into the bathtub, and you turn on that water so it's the same rate as the amount that's leaving the bathtub, then the amount of water in the bathtub is going to be the same. So since the Industrial Revolution, we have been turning that faucet on more and more, but the drain has not really been changing. In fact, if anything, we're making that drain smaller by removing forests and things like that. So we did reduce that faucet flow a little bit during the pandemic, but it's still bigger than the water that's leaving the drain. And so we're still seeing an increase in the total amount of carbon dioxide in the atmosphere. So yes, it helped a little, but it's so far from what needs to be done.
So I think this is kind of a related question. Bernadette Engelstadt asks about, is research being done on the effect of technology, radio waves and radiation with cellular and wireless technologies? Does that have an effect on global warming? And I'm a physicist, so that might be more in my bailiwick than yours. I would suggest
the short answer is no.
Yeah, I actually think it helps us because with wireless communication, and particularly 5G and the capacity, remote work and communications reduces the need for particularly international travel and commuting. And so that can only be one of those small but important contributions to just reducing the production of greenhouse gases.
Right, I agree.
Yeah,
but the radiation itself has zero impact, or the effect would be so tiny it's not measurable.
So Annie Clotter asks, have there been models made that deal with artificial modifications of cloud masses to lower temperatures? And the idea of using something to artificially increase the albedo to reflect solar radiation back into space. I guess this is a geoengineering question.
All right. Yeah, people are working on that. It is an interesting question to explore with research. There's no doubt that if we could somehow put dust particles up in the atmosphere, it would have a cooling effect, because we see examples of that in the real world when a volcano erupts, especially a really big one that can put particles very high up into the atmosphere so they don't get rained out right away. It's clear that the Earth will cool for some period of time, a little bit. But also, it's, if we could somehow increase the whiteness of the ice in the Arctic, it could probably help for the Arctic ice to at least slow its melt somewhat. The problem with all that, though, is that if you start these programs, it's really just putting a Band-Aid on, somebody with cancer, you put a Band-Aid on their arm where they got some injection or something like that. If you don't treat the underlying disease, all of these other efforts are going to be very expensive. They are going to, I think, detract from treating the real disease. It's taking resources away from figuring out ways to transition to a renewable energy economy. And there's a lot of uncertainty about what might happen, inadvertent consequences of doing these sorts of things, where because we just can't predict exactly how the atmosphere is going to respond, it could set up terrible droughts or terrible floods, or, and if it happens in one country and they blame another country for doing these particles in the stratosphere or whatever, I mean, it could cause a lot more problems than it resolves. And so my view anyway is that we should focus on treating the disease, not some of these Band-Aid solutions.
Yeah, absolutely. It also doesn't address the issue of there's more carbon dioxide particularly in the oceans, with all the impacts that has on the ocean ecosystem. And I love mussels, and I do not want to see them disappear.
I agree.
So it's getting close to 8 o'clock, which is sort of close to our traditional end time. So there are a couple of questions. John Bullard and Ken Fitt asked, what can individuals do? Are there local organizations and groups and people that can get together and do things? And also, to John Bullard's question, what should we be telling our representatives in Congress to do? I mean, you said that President Biden's proposals are a start, but they don't go far enough. So I think it's on us, the people, the public, to put pressure on our representatives and move the United States in the direction that we know we need to go.
Well, I totally agree with that. I always tell people the most important thing we can each do is vote for leaders who understand that this is a crisis. This is a huge problem, and we have to get people in leadership positions who are willing to perhaps sacrifice their political careers for their kids and their grandkids and, all of the good of the planet, without being too trite. But on individual levels, we have voices. We do need to make sure our leaders know what we want. We have to tell them that they have to hold emitters accountable. As I said, these, especially the fossil fuel companies, have been dumping their garbage into the atmosphere without having to pay for it. And it's time that they have to start paying the price. And there are definitely ways being proposed where the average consumer doesn't see a big increase in energy costs. And instead, these companies that have been making so much money off of both providing fossil fuels and also the infrastructure for fossil fuel delivery. I mean, we know that we can get off of fossil fuels now. We have other ways to provide our energy. So we definitely have to make ourselves known in terms of our leaders understanding this is the direction we want to go. But we all have to do our parts too, as we said in the beginning, where we have to think about, do we really need to fly to Las Vegas to attend a meeting for half a day? Do we really need to get in our car and drive an hour to get a certain thing at a particular store? We can reduce how much energy each of us uses. And if we really think about it, every step of our day, really, because by not using energy, let's say every electron that we cannot use, we're actually saving several, because it takes a lot of energy to make energy. And so, we each can do our part, and that's probably one of the biggest things. And you've all heard about, eating less meat and, kind of modifying our behavior, not drastically, but, if we all did something, it would add up. It really would.
Well, thank you, Jennifer, again, for an absolutely fascinating talk this evening. I hope I've grabbed everyone's questions and caught them. If I haven't, just please send them again to us in the chat, and we'll forward them to Jennifer and see if she can answer people's questions. So thank you again, everyone, for coming this evening. Robert, do you want to remind people of next month's Science Cafe?
And I'll note that Jennifer, your friend Beth Davis asked for that 20,000 years slide. So if you could send that to her, apparently you already have her email address. So on behalf of my colleague, Jocelyn Nunes, the behind the scenes guru for Zoom from the New Bedford Whaling Museum, and our president and CEO, Amanda McMullen. By the way, it's nice to see a nice showing of Whaling Museum members, trustees, and volunteers and our participants tonight. We hope that you will join us on Tuesday, March 2nd, when ornithologist Alan Poole will join us live from Costa Rica to talk about the Quetzal, birds as barometers of land use in Central America. We thank all of you for your questions. Grant, thank you for your deft handling of questions, and Jennifer for your very thorough answers. This has all been great. And as Jocelyn has noted, this is recorded. It'll be available on the museum's YouTube channel within the next couple of weeks. It'll be under our New Bedford Science Cafe playlist. So again, thank you all for your participation and for joining us tonight, and have a wonderful evening. And stay warm and use as little energy as possible doing it.
Thank you, Robert. It was a wonderful evening.